This conference will now be recorded.
So, very good evening, students. Today we'll be learning about various circuit configuration or transistor configuration. In various configurations, transistor can be run or can be used. So, we'll discuss. So, what are those, and we'll take up a particular one today to discuss, and then I may take different configurations in different classes. So basically today what we'll do, we'll learn about transistor characteristics in a particular configuration. Transistor characteristics, we had already learned what is meant by characteristics. So characteristics means a set of curves or set of graphs. So as we have seen in case of diode, we had seen forward bias characteristics, okay, and reverse bias characteristics for diode. Similarly, in this case, in transistor also we'll learn about characteristic curves of transistor. Okay, so before I go to that, I'll just recap little bit about the transistor whatever we had learned in the last class. So we know this is a three-terminal device, solid state device. So those are like three terminals. The terminals are emitter, then you have base and collector, okay, EBC. Emitter, which will supply the charge carriers, majority charge carriers for the transistor operation. Base will act as the junction of this E and C, collector and emitter that we have seen. So here in this case, see, this is the emitter and this is the base and collector. We had discussed different amount of doping and different shapes and size for emitter, base and collector, etc. And we had discussed two different types of transistors, NPN and PNP. So it depends, like when you use N-type semiconductor as emitter, base as like P-type semiconductor as base, and again collector, you use another N-type semiconductor, then it is called NPN transistor. And PNP transistor similarly we can define. And what we had learned in the last class is the most important thing, that the operation of the or action of transistor we had discussed with NPN transistor. So we'll be again learning how to bias a transistor. We had already learned a little bit how to bias a transistor, like here NPN transistor. So we had two different types of battery, VEE or VCC. So since it has three terminals as we had seen, NPN or emitter, base and collector, so it has actually three terminals. Okay, three terminals. For operation, what we had to do, so for transistor operation we have to take any one of the junction, sorry, any one of this collector, base or emitter, we have to take as common, and then we have to make it ground, okay, or we have to give zero potential. Okay, so if I say common base, then base can be connected with with a battery with emitter. Okay, this is, and this part is called input part. Okay, this is called input. BE junction. BE junction is called input, and CB junction, collector base junction, is called output. So you can see there are like three different terminals, but we have to use as input and output. So I need to connect a battery. Like battery positive terminal has to go to emitter, and the negative terminal will go to the common one. Common one, it can be here. I have taken base as common. Some cases you can take collector as a common. Sometime you can take emitter as common. So depending on that, there are different configurations. Today, actually, main thing is that there are different configurations. As I said, you have emitter, then base, and collector. So these three terminals, I have to take one, like two at a time. Okay, to bias with connecting, like by connecting with external battery. So I can take B as a common, base as common, then I can bias with battery. So this is called common bias circuit. When I common base, this is called common base circuit. So this is abbreviated as CB. Okay, common base circuit. Okay, now if I take emitter as the common terminal, then look, this I can connect and this too I can connect. So E always negative or zero potential. Here it is positive. Again, this is also positive terminal to the battery. Okay, this is how. So this configuration is called common emitter. So C for common, E for emitter. Here C for common and this B for base, common base configuration. So I can have similarly common collector also. Okay, I'll write. I can have common collector circuit. Okay, when I take the collector as common, then it is called common collector, CC, common collector. C for common, another C for collector. So there are three type of configurations basically: common emitter, common base, and common collector. So these are three different types of configurations. We will discuss today about common emitter configuration. Okay, so common emitter configuration, what we will do in this, we will see how to bias the common emitter, like how do we connect the battery and other devices, okay, circuit elements with the circuit diagram, common emitter circuit diagram. Then we will see what is called input, what is called output. So in the transistor there are three terminals. One terminal has to be common, used as input as well as output also. Okay, let us see common emitter circuit here. See, common emitter, and this is NPN transistor. Generally common emitter configuration is being used widely along with that NPN transistor. Common emitter, NPN transistor with NPN transistor. Okay, so NPN transistor means, see, N is here, N type. Okay, so N type is emitter here. See, N type, emitter is N type, base is P type semiconductor, and collector is again N type semiconductor. So I have taken NPN transistor and connected or made the circuit diagram in common emitter configuration. Okay, look here. As I said, common terminal has to be grounded. Look, this is emitter. Okay, this is NPN transistor. So you might be remembering that the circuit diagram for a, a transistor is done like this. So this is base. Okay, uh, so there are three terminals, right? Like that we have to, but there should be an arrow. If it is NPN transistor, then the arrow will be always outward. Okay, outward. So that is what you can see here. This is the one. Okay, so arrow is given out. So this is NPN transistor, and in case of PNP transistor, in case of PNP transistor, base. See, there are three terminals in this case also. So you have to properly put the arrow. This arrow only will determine whether it is PNP or NPN. So P is the emitter. So this is emitter, and N is the base. So your arrow should be inward or towards base. Sorry. So I'll just redraw maybe. So oh, I'm sorry. Like that it is drawn. So if it is PNP, then your arrow should be inward towards base. So this is emitter, this is base, and this is collector. Okay, so this is the circuit diagram. We have taken emitter as common. Look, then this is the emitter which I have grounded. So this is common emitter. Now see, this emitter, common emitter means what? I'll be using this emitter both at input junction, like when I'll do input biasing, and when I do output biasing also, I'll be using that output biasing. Now we'll see which junction is called input and which junction is called output. Look, if I have, see this CE configuration, this one is input BE. Okay, so BE junction is input junction here. BE junction is input junction. Input junction. Input junction. Okay, and CB. Okay, sorry, here it is BE and this is CE. CE is here output junction. Output junction. BE and CE. There are two junctions here. Okay, so BE is input junction. Okay, all right. So today, as I said, we'll be discussing about the characteristics curves. So we have seen BE and this is CE. Okay, so there are two junctions. One is input junction, another one is output junction. So input junction is connected to a battery. See, you can see that VBB. Okay, input junction. So it is, see, the battery terminal, positive terminal is connected to the base. So I have taken NPN transistor, C configuration NPN transistor. So the base is actually P terminal, P type semiconductor. Okay, base is made of P type semiconductor. So the battery positive terminal is connected to base, and see the negative terminal of the battery of VBB. So VBB, this is a battery. This is denoting a battery, and corresponding voltage is actually VBB. Okay, so this is the battery, external battery. And see, with this we can bias the input junction. We are biasing this input junction by a battery BB, and voltage which we are applying across this junction is called VBB. Okay, total voltage. All right, and see, this is actually a rheostat connected so that you can vary the voltage, biasing voltage. Now the output junction is C and E. This junction is actually biased by VCC battery. VCC battery. So in this case, you look the NPN. This is N-type semiconductor. Collector is N-type semiconductor. This is connected with positive terminal of the battery. So you can see here that when the P junction is connected, or P side is connected with positive terminal of the battery, and N side is connected with negative terminal of the battery, then it is called forward bias. So the input junction is forward bias. You can see that input junction is forward bias. So input junction is forward bias, and here reverse bias is the output junction. You can see that NPN, that means the collector is made of N-type semiconductor, and that is that is connected to the high voltage or positive voltage of the battery VCC. That's why this is, so I'll write input junction is forward bias. Okay, and output junction, here input junction was BE, here it is CE. Output junction is reversed biased. Okay, reversed biased. All right, so this is the biasing part. Now here you look, what else you have a voltmeter to measure the input voltage. Okay, then you have a microammeter, as we have seen in the transistor operation part. So total emitter current is equal to the sum of IC plus IB, but this IB, the base current, is actually very negligible, very negligible, because only 5% of carrier gives rise to the base current. Okay, and 95% goes to collector, and they give rise to collector current. So that's why this current is very negligible, of the order of microampere. It has of the order. So see, the base current has order, or base current is very small current. It is almost negligible current, 10 to the power minus 6 microampere. That's why here, to measure the current, microampere is being connected with the base. Okay, now emitter, the collector current is comparatively large, because 95% charge carriers will be collected by the collector. Therefore the current is much larger. Okay, much larger. So therefore, milliammeter, but the much larger in the sense the current is much larger than the base current. Collector current is much larger than base current. So to measure the collector current, milliammeter has been used. Okay, so these arrows are actually indicating the variation actually. So this is kind of a rheostat you can use, or potentiometer to vary the voltage. Okay, so if you vary this VCC, then look what will happen. It will actually, it is actually connected to VCB, this much, and this much voltage VCE. Okay, VCB and VCE. Total VCC is equal to VCE plus VCB. Okay, so this is about circuit diagram for the characteristics to draw. Now we'll as we have understood that there are two types of, okay, let me tell you. So since I have to bias two junctions, one is input and another one is output. Okay, output. So there are two types of characteristics curves we'll be drawing here. Input characteristics. So there are input characteristics. I'll discuss you what it is. Input characteristics and output characteristics. Obviously another also we can discuss today, that is transfer characteristics. Transfer characteristics. So there are three types of characteristic curves which we are going to study today. Okay. So let me tell you what is input characteristics in the common emitter configuration. So input characteristics, you can see here in this graph itself that the input characteristics are the graphs showing the variation of base current IB with the emitter base voltage or base emitter voltage at constant collector emitter voltage, at constant collector emitter voltage. They are called actually input characteristics of the transistor. And you can see that only one curve has been drawn. I'll discuss why one curve and why VCE has to be constant. Those things we'll discuss now. See, what is input characteristics then? Input characteristics is the variation of okay, let me write graphs. These are the graphs showing the variation of base current because base emitter junction is the input junction. So variation of base current IB with respect to the VBE voltage. This is actually called base emitter voltage. Base emitter voltage at constant CE or base constant collector emitter voltage constant at constant VCE or collector emitter voltage. Okay, so input characteristics are the graphs showing the variation of base current IB with respect to the base emitter voltage, that is VBE, at constant collector emitter voltage. Okay, now let me tell you why VCE has to be constant. Actually, look, VCE, if I write VCC, this will be equal to VCE. Look here, VCC. VCC means this VCC will be sum of VCB plus VCE. Okay. VCB. Okay, this one. Or if I write VCE alone, VCE, this will be equal to VCB plus VBE. I'll show you why. See, VCE is the total voltage. Okay, look, concentrate on this. VCE, this is the total voltage across this junction. So this can be actually subdivided into two. This is the B. So this is junction, one junction. So there will be drop across CB junction, and there will be drop across BE junction. So this will constitute the total VCE voltage. Okay, so then let me not confuse you with this one. So I hope I could make you understand why VC is equal to VCB and VBE, because VC is the total voltage across CE junction, which can be written as the voltage drop across CB junction and BE junction. Now when VCE increased, then VCB also will increase. Okay, VCB also will increase. So which will affect the base current. Okay, so base current will be affected by VCE voltage. So that's why VCE, when we are seeing the variation of IB versus VBE voltage, VCE has to be constant, but at the same time it has very negligible effect, not much. Okay, it doesn't affect too much. Okay, it affect negligibly small. That's why if I draw curves IB versus VBE, making VCE voltage constant, some constant voltage, suppose here for VCE 10 volt, the IB versus VBE, you can see this VBE, and here it is IB, as you can see. So VBE and this is IB. When we draw a curve between IB and VBE, we have to keep VC fixed or constant. Okay, so if I draw many curves keeping VCE constant, suppose here it is 10, I can just keep another VCE constant, some 15 or 20 or whatever. That would not change the nature of the curve. That would not change the nature of the curve. Okay, so that's why only one or two curves are generally drawn. Input curve only one or two, sometimes two also people can draw. So one or two input characteristics is drawn. Okay, here only one. For only one VCE constant, that is 10 volt. Now look one thing here. What is the nature of the curve? See, see what we are doing. Input means what? So there is BE junction, B and E junction. So here it is NPN transistor. So N is emitter and base is P. So this is basically a PN junction. This is basically a PN junction. And you can see here this BE junction has been biased as forward bias because P is like base is P type semiconductor, and that P type semiconductor is connected, or P side is connected to positive terminal of the battery. So effectively the circuit is becoming like this. You have, sorry, BE junction. So B and E junction. First is B, B is P, and this is E is N. So look, this is actually forward bias, PN junction. Forward bias PN junction. So here the voltage is VBE and the current we get is IB. Okay, we have to draw the characteristics for fixed VCE. So this is the situation. Look, in normal diode, what we have seen, in suppose here it is silicon diode, silicon NPN junction diode, sorry, transistor, silicon NPN junction transistor. So this is made of silicon, means VBE, this voltage will be a fixed value generally for like barrier voltage, barrier potential for silicon at the BE junction or forward bias case will be 0.62. It varies from 0.6 to 0.7. That means what? Barrier potential at forward bias in case of PN junction for silicon is 0.6 to 0.7. That means what? Below any biasing voltage, any biasing voltage below 0.6 or 7 would not be able to make this PN junction to flow any charge, or there will be no current. Okay, as you know, forward bias in ideal diode, forward bias gives, like, it conducts, and reverse bias it doesn't conduct. And in forward bias also, if your voltage, biasing voltage is below 0.6 or pure below 0.7 voltage, then there is negligibly small current, almost zero current, you can see. So this is similar to forward bias PN junction diode characteristics. You can remember this. See, this is kind of forward bias PN junction diode characteristics. Okay, so kind of forward bias PN junction diode characteristics. So in that case, what we see, until the voltage is going beyond a certain voltage, that is called cut-in voltage, here it is 0.6 for silicon, you will get current negligibly small, that can be treated as zero also. So here is no current till 0.6, and when your biasing voltage increases little bit beyond 0.6, then slowly current increases, and as you increase and increase, you will see after some time the current will be current will be increasing very sharply. So this portion is almost linear portion. So there are, see, this is non-linear portion, and see, when the current is increasing rapidly with the applied voltage, and that would happen beyond this cut-in voltage 0.6 volt. So at that time we get almost linear curve, as you see, almost linear curve at high VBE voltage. So at this linear part we can use to calculate the input resistance. So what is input resistance? So this is IB versus VBE curve. So reciprocal of the slope will give you resistance, right? Reciprocal of the reciprocal of the slope of the curve will give you resistance. So resistance R input is equal to delta VBE, change in the voltage, divided by corresponding change in the base current. Okay, corresponding change in the base current. So this is input voltage. Obviously there should be VCE constant, and there will be a slight change in the value of this voltage for different VCE. Okay, nature may be the same, but absolute value will be greater than like differing for different VCE voltages. Okay, so this voltage, since the current is changing along with the voltage, see, and this change in the VB divided by change in the current, this is actually called input resistance, but this is called dynamic resistance because it varies. This value actually varies. So that's why it is called dynamic resistance. Okay, so input resistance, and it is called dynamic resistance. And input resistance can be of some hundreds to sorry, some hundreds to some hundreds of ohms. It can be of some hundreds of ohm input resistance. Okay, input resistance can be of some hundreds of ohm. Okay, so I hope it is understood. So the input characteristics is drawn IB versus VBE when VCE is constant. Okay, VCE is constant, and it has a characteristics similar to the forward bias PN junction diode. Below 0.6 or 0.7 there is negligible zero current, and when the voltage is increased beyond 0.6, then there will be increase in current, and if you further increase the voltage, then you get a linear increase in the or proportionate increase in the current with the voltage. Okay, and this linear portion can be used to calculate the input resistance, that is delta VBE divided by delta IB is equal to RI, that we have seen. And the input resistance can be of some 10, 100 to hundreds of ohm. Okay, hundreds of ohm. All right, so this is input characteristics. And now we'll just go to the output characteristics. So this is very interesting. We have to first understand that what is called output characteristics. So I'll just go to this circuit again. See, as I said, the BE junction was input junction. Okay, BE junction was input junction. And CE junction is output junction. Okay, output junction. Here it is input junction. So here in the output, what are the current? Current is IC. And what is the voltage? across TCE junction, that is VCE. So then we have to see the variation of collector current with respect to the collector emitter voltage. But here uh, one thing you have to keep constant is that IB. So we have to draw draw IC versus VCE curve for different values of IB, some non-zero value, 10 microampere, 50 microampere, then 100 microampere for different values of base current. But why base current? Okay, look, we know IE is equal to IC plus IB. This we know, right? All right, we know that. But you look, we had written previously also. So VCE, this means VCB plus VBE. Okay. So this VBE is very less for silicon transistor, almost 0.7 volt or 6 volt, 0.6 volt. So okay, one more thing I just forgot in the input curve. I just want to mention once. So this VCE voltage has to be kept fixed with the within a value 3 to 20 volt. In this range, any volt you can take and keep constant, and then draw the input characteristics. So here output characteristics we will be drawing. We will be drawing curves IC versus VCE when we will keep IB fixed. For IB fixed value. Okay, why? Because if the VCE increases, then VCB plus VBE, VBE anyway constant 0.6 or 0.7, but VCB, this would actually affect the base current also. This will affect the base current. VCB also affect the base current. So as you increase VCE, see, this VCB increases, therefore both IC and IB changes. Okay, both IC and IB changes. So in this case, that means that means input is affecting your output. That is what I want to say. Input current is affecting your output current. So that's why you have to draw output characteristics for different fixed values of base current. Different fixed values of base current. See, I can take base current 10 microampere, 20 microampere, 30, 40, 50, 60 microampere, like that. Whatever number you want, you can draw those many characteristics, but with fixed value of base current. As I said, base current will affect the collector current also. So that's why. So here the variation of collector current with respect to collector emitter voltage. Now in this case, if you look the characteristics, this is IC in milliampere and this is VCE in volt. So you can see there are three distinct regions in this characteristics curves. I'll tell you. Before that, let me tell you what we are doing here. We are drawing IC, keeping IB as fixed value and increasing the VCE voltage. So look here, when VCE is increased, then up to certain voltage, see, I'll write this equation: VCE is equal to VCB plus VBE. This has a fixed value 0.7, suppose 0.7 voltage. So okay, so when you increase the VCE, but VCE is well below this 0.7 or zero point 0.6 voltage, okay, then the current will be increasing almost linearly and very rapidly it will increase, and it will be actually a function of VCE. IC is only function of VCE, and in this situation you can see that both the junctions are forward bias. Collector emitter junction is forward bias, and base emitter junction also will be forward bias. Okay, so that's why when both the junctions are forward bias, both the terminals are forward bias, input and output, then that is called saturation region. So you can see this curve, okay, this shaded region, this is called saturation region. This is actually this happens below even this much voltage, below 0.7. Below 0.7, VCE increases linearly with IC. I'm sorry, IC changes linearly with VCE. Okay, and it has a rapid change. So this region, shaded region, is called saturation region. This indicates that the current IC is only varying proportional to VCE. There is no effect of the other voltage VCB. Okay, sorry, VBE, because VBE you need greater than 0.7 volt, then only it will be actually conducting. So before that, only see, IC is a function of only VCE, applied voltage. Therefore it will increase linearly and rapidly. So you can see this portion will be linear like this. Because of this line you cannot see, so this is called line of saturation, and this region called saturation region, because both both the both the E and emitter and collector are in forward bias, okay. So this is called actually saturation region when both the junctions are forward bias. All right, now you see, beyond certain voltage, that is maybe 0.7 or 0.6 volt, beyond certain voltage, what happens, the current actually grows slowly and it shows a kind of neck, okay, kind of knee it shows, and then it's the current remains almost constant. Okay, IC remains constant, almost constant in this region. For different values of IB you get greater IC you get, but the variation, you look this here, there is no variation in the collector current, it has got almost a constant value. So in this region, you know what happens in this region, when you increase the VCE beyond some 0.7, okay, or 0.6, then your collector junction is going to be reverse biased, because look, VCE is equal to VCB plus VBE. Your this current is much, see, this voltage is greater, means this is already forward biased. Now this also will go to reverse bias. Okay, therefore one side, see, input junction will be forward bias, BE junction will be forward bias and collector emitter junction will be reverse bias. At this situation, the IC, the current IC gets a almost constant value, but it will have increased values compared to 10 microampere. In 20 microampere base current, you will have greater IC value, but in this region it will be almost constant. So this region is called active region. Active region. In active region, base emitter input junction is forward bias, output junction is reverse bias. Now another region here you have, that is this region. You can see this one below IBC. If you just put IB is equal to 0, then your current IC also will be 0. Okay, IB 0 means IC also 0. So when IB is 0, then both the junctions are cut off at cutoff region. That means both are reverse bias. Both junctions are reverse bias at this condition. Junctions are reverse biased, RB. So when both the junctions are at reverse bias, then you get no current, no current. So IB is equal to 0 means IC is equal to 0, no current. So this is called cutoff region. That happens below, below IB is equal to 0. That region is called cut-off region. Okay, cut-off region. So there are three regions in this characteristic curves. One is actually the saturation region, then you have active region, and then you have cut-off region. So when the transistor is used as amplifier, then transistor has to be operated in this region if you want as amplifier. Okay, as an amplifier, then your transistor has to work in this region. That means your VCE value has to be put such a value that it will be greater than 0.7 volt, and then both the like reverse bias will be like collector emitter junction will be reverse bias, and base emitter junction will be only forward bias. So this would give you the condition for active region, or this region when input junction is forward bias and output junction is reverse bias, your transistor is in active region, and at this condition you can use that as signal amplifier. Now if you want to use the transistor as switch, see, you can use this region cutoff and this cutoff cutoff and saturation. Cutoff and saturation, these two situations are used in case of switch action of transistor. Switch action. So transistor is operated either in saturation or cutoff region when we use as switch. Okay, so saturation maybe tell you the off. You can just define off and on region, like off and on conditions you can define by your own, and according to that you can use the transistor in two ways. Then one is as an amplifier, signal amplifier, and second thing is as a switch. So switch, when we use the switch action, either the transistor has to be operated in the saturation or in the cutoff region. But when you used as amplifier, that time you have to operate the transistor in the active region. Okay, so in the active region there will be, say if you draw some line like this, okay, then you get a middle point that is called Q point, and it has IC, VCE coordinate and for constant IB. Okay, you have this coordinate. So these are the values which determine whether the transistor is in the active region or not. IC and VCE and also IB base current. Okay, so all right, this is about transistor characteristics. Now in the transistor characteristics, as I said, the linear portion of the curve can be used to define or calculate output resistance. So output resistance here, delta VCE divided by delta IC. Okay, change in the change in the collector emitter voltage to the change in the corresponding collector current. So this is the ratio. This obviously this will be for a particular IB, non-zero value IB. So for a particular IB, so IB has to be constant, and at this condition you get the output resistance. And what are the range of output resistance? Here also you get some thousands of okay, so I think I had just given you a wrong information over here. So here it will be 100 to 1000 ohm in case of input, some 100 to 1000 input resistance. Okay, Ri ranges from some hundreds of ohms to some thousands of ohms. That means some 100 ohms to kilo ohm range. But in case of output resistance will be some tens of ohms to some hundreds of ohms you get here. Output resistance is comparatively less than the input resistance. Here we'll be defining another term, another like there are. So as I said, there is amplification. So we'll be defining a parameter which is called current amplification factor, and then I'll stop. Okay, we'll define current amplification factor. Current amplification factor. Current amplification factor. So this is denoted by beta AC or beta DC. Okay. So current amplification factor is defined as the ratio of change in the collector current to the small change in the base current. Okay, to the small change in the base voltage. I'm sorry, beta AC. Let me write this beta AC. This is actually current gain means IC small change in the change in the output current or collector current to the small change in the base current. Okay, it is the ratio of the change in the collector current to the small change in the base current. And see, when it is actually obtained from output characteristics only, so obviously here you have to have VCE constant for some constant VCE voltage. Okay, or let me write as const. Okay, so for VCE constant, some constant value, if you get the ratio of change in the collector current to the change in the base current, that will give you beta AC. This is called amplification factor or current gain. This is called amplification factor or small signal current gain. This is called small signal current gain. Small signal current gain. Okay, so when we write this ratio, simply IC by IB, then it is called beta DC. Beta DC. Okay, beta DC, IC by IB. And more we'll see that beta DC and beta AC, they have values more or less same. Okay, more or less same value you get, beta DC and beta AC. That's why most of the time we will be using beta DC in our various parameter calculations, okay, or gain calculation, beta DC. So we can define either beta, beta means current gain. Either we can define that as IC by IB. When I write IC by IB, then it is called beta DC. And when I write delta IC by delta IB, this is called beta AC, but their values are almost same. Okay, so that's why, or nearly equal. That's why we can use beta DC for various calculations, or any one of them we can use. Okay, so beta DC and beta AC more or less having the equal value. Okay, we'll stop it here for today. So next day we'll take off transfer characteristics. Transfer characteristics means when you draw a curve between IC and IB, output current versus input current. Okay, so that is called transfer characteristics. So not only current, you can even do with voltage also, output voltage with respect to input voltage. Okay, so that is called transfer characteristics, and we'll see how transistor can be used as a switch first in the CE configuration, how we can use a transistor as switch, and thereafter we'll see how CE configuration of NPN transistor can be used as an amplifier. Okay, so those things we'll learn back to back. So today we'll stop it here for. Okay, so bye for today.